Hello and welcome to Hack to School. I'm Dan Costa, editor-in-chief of PCMag.com, and I'm joined by JonAlf, Darlin Weaver, who's the coordinator of computer science at Stuyvesant High School, and we are going to show you how to code.
That's right. This is our last session together right now, and I've got a number of things I want to show, and I'm really excited to do that.
Before we get to it, I want to thank our partners with Lenovo. Hack to School is a partnership between PCMag and Lenovo. They've done a great job of donating Lenovo Yoga 910 laptops. We've got a variety of students across the country watching us right now. I want to say thank you and hello to Kensington High School in Philadelphia, to Bayonne High School in Bayonne, New Jersey, and Lakeview High School in Chicago. Thank you for joining us. Thank you for hopefully watching all of our shows. This is the third show that we've done this.
Yeah, thanks to everybody watching. I hope you've enjoyed it and learned some stuff about coding. So
I want to just let our audience know there's a couple things we're going to do here. John's going to give a presentation. We're going to learn how to code. It's going to build on the previous shows that we've done. You can go back and watch those as well. If you have questions, you can ask them in the comments section right below this video. We will answer them live on air. We'll also answer them throughout the day. So if you have questions we don't get to on air, we'll answer them later on today, even tomorrow. And then at the end of the show, Will Greenwald's going to be here. He's going to be showing, he's our robot expert here at PCMag Labs. He's going to be showing off some really cool robotic tools that you can also control using programming.
Yeah, I'm really excited to see what he has. He showed a little bit, and it looks exciting.
So let's move on to, this is our third, probably the most sophisticated class that we've done so far.
Yeah, so I'm going to do things a little bit differently today than what we did in the previous two. I'm going to go a little bit faster, but I want to try to show some of the things that are really possible in NetLogo, and I think that's important.
And so NetLogo, just for people that are joining us for the first time, explain what NetLogo is and how it works.
So NetLogo is a programming environment where it looks like what we have back here on the screen there. And basically you interact with either turtles or patches, and turtles can move around and patches make up the background, and you can program each of them individually and command them all to do something at the same time, and lots of really cool stuff can occur, and that's what we're going to see today.
Very cool.
Yeah. Starting off, those of you that have seen our previous videos will remember the swords from the last video, and I just wanted to go through one more thing about image processing, and so this is going to be less about the code that makes this process happen, but more about a very important process of computer programming, which is algorithmic thinking. We've talked a lot about how to make things happen, make the turtles do this, but usually what happens in computer science or computer programming is you have a problem and you want to solve it. And you say, well, I know how to program. I can do something there. And how do you go about coming up with the solution? And in programming, the solution is almost always in the form of an algorithm. And an algorithm is a fancy word for steps in order, right? If you've ever cooked or used a recipe, like that's an algorithm. It tells you what you need and then says do this, then do that, and then whatever. And that's what an algorithm is. We're listing the steps to solve the problem. So a common image manipulation problem is what's called edge detection. You've got an image like this, say, and the image has lots of features. Well, not too many actually. It just has these three big swords. But there's lots of gradations in the color in the background, and down here and the trees and all that. And sometimes you don't want all that detail. In instances like, say, computer vision or things, you want the computer to be able to recognize certain kinds of shape. Or when you use a camera and you do sort of face detection, right? It doesn't need all of the information. It just needs to know what generally a face looks like and get rid of a lot of the little details, right? So edge detection gets rid of those details and saves the edges, is the idea. And so I have an example here, and I'll show you the code very quickly. I'll talk about the algorithm, because it's actually pretty straightforward. By
the way, props for using swords to demonstrate edge detection.
Yeah,
well done.
I've got, I do a lot of puns in my class. I'm proud of it, actually. Let's own it up. Yeah. So I just pushed this edge button, which is attached to a procedure in the back, and you'll notice everything became one of two colors, right? It became either black or white, and the white portions are the edges, and the black portions are the things deemed not edge-worthy. And notice I can still tell what this image looked like, and I can even pick out the shapes of the swords a lot better. And so the way that this algorithm works, because this is what I want to talk about, not so much the code, is every patch, so I'm going to push reset, take us back. Every patch has the ability to look at its neighbors and say, hey, what is your color? And how do you know if something's an edge? Well, if the patch looks at its neighbors and says, oh, wait, your color is significantly different than mine, then it must be a border. And then we say, all right, if you think you're a border after checking your neighbors, then you're going to become white. If you check your neighbors, like somewhere over here in this sky area, and you find out you're pretty similar colors, then you're going to turn black, because it's extra detail noise that we don't need. And that's how edge detection works. It's actually straightforward. It says, all right, look at all your neighbors. Compare your color to them. If you're close in value, then you're not an edge. If you're far in value, you must be an edge. And we know colors are numbers from last session. And then if you've decided you're an edge, turn white. If you decided you're not an edge, turn black. And that's it.
So that's that's sort of the plain English explanation for what's going on.
Yeah.
How do you convert that into code so that the system can actually run and execute that command?
So I'm not going to go into too much detail because there are a few things that I could spend the whole time talking about that in NetLogo. But I will put the code up, and anybody watching, I've made it big. You can see it. You can pause the video and check it. But you'll also see there's not a lot of code, right? And because NetLogo is somewhat English friendly, a lot of it makes sense. So moving straight to this calculate. I gave patches a property called diff for difference. I'm a little lazy, so I said diff. And I said, all right, the difference is going to be the sum of the p color of your neighbors divided by however many neighbors you have. Okay, so that it's weighted. And then I'm going to say, change the diff, set diff to whatever that original color value of your neighbors were, minus the p color, your p color. And then we do an absolute value because we don't need negative. I don't care if it's a positive or negative difference. I just care how big is the difference. Right? So that's calculate. And then this edge detection, I ask the patches to calculate, and so everybody calculates first. And then I use the if-else statement we saw last week, and I say if-else diff is greater than tolerance. Where did that value come from? This slider here. And if the difference is greater than the tolerance, we're going to set the p color white, because you must be an edge, or you set your p color black. And that's it. That's how it works. And so we can actually see the difference. Right? If I set my tolerance really high, and I do edge, notice there are fewer edges, because now I'm saying, oh, there's a larger range of accepted values to be nearby. I can also set the tolerance really low, and do a reset. So I don't want to do an edge detection on an edge detected image because there's not much there. Really low, and I click edge. I click edge. There we go. And you'll notice there's a lot more fuzzy detail, right? And so with edge detection, it's a sweet spot. Like that 30 value worked pretty good. I did it beforehand and checked. So that's this thing called edge detection. It's an image process. It's an algorithm. And I think teaching about computer programming and not discussing what algorithms are and giving an example of one would been bad on my part. So I wanted to go through that.
And also, I mean, you wrote that yourself from scratch.
Yes.
But if you want to understand how algorithms work, there's lots of examples. Like you could find somebody, if you wanted to do edge detection, you're using NetLogo, you could probably find some examples that you could borrow from.
Sure. Yeah, there's lots of...
Steal completely?
Steal, borrow. Well, you credit it, and then it's okay. And so that's one of the things I want to show is, now that I've gone through that, I want to show two things importantly. One is resources, how to learn more about NetLogo once I'm gone from these, and what is possible. Because I think those are a lot of the questions that we've had over the past two sessions were along the lines of, all right, how do I learn more, and what can I do? And so I wanted to focus a lot on that.
Yeah, let's do it. And now, while you're setting that up, I want to remind our audience, if you have questions, let us know. We will answer them live on air. We'll also answer them later after we're off air. But while we're here, we will do our best to answer those questions. Social Pete is in our message boards right now, monitoring them. So if you've got questions, let us know.
Yeah. All right. So I just switched out to the internet here. and I went to the NetLogo homepage. If you just Google NetLogo, you'll find it. It'll show up. And there are two amazing resources on the NetLogo webpage. So first, on the side here, user manuals. Let's click web because, hey, it's the internet. And it may not be the world's prettiest site, but it's got so much great information. So on the sidebar, we've got what is NetLogo, tutorials, learning through various things, references, and so you can follow through and learn a lot about NetLogo. What my big resource here is what's called the NetLogo dictionary. And if I click on that, you'll see this contains every single command built into NetLogo. Organized by turtle-related, patch-related, and observer. There are agent sets, all sorts of things. So like I can check out, let's go to one that takes an argument. What do I want? Forward, right? So if I click on forward, I swear I did. Notice here we have forward, the shortened version FD, forward number. The little turtle thing says, hey, it's a turtle procedure. And then the turtle moves forward by however many steps, so on and so forth. And an example, okay? And it tells you any like special cases, right? So that's just one command. But basically, every command in NetLogo, you don't need a textbook, you don't need external resources. They're all right here, which is one of the reasons why I decided this would be the best place to start, because there's so many resources and you don't have to look far, all right? So that's the NetLogo dictionary. Just wanted to show that because you want to learn more, come to the NetLogo webpage and you've got all of the information you need.
You get your commands. There's probably algorithms here as well.
Yes, yes, in the models, examples, and this extension guide and all this stuff. So that's one resource. Another resource I'm just going to show very quickly is if for some reason you have trouble downloading NetLogo, like you want to learn NetLogo, you want to do it, but you have trouble downloading it. There's this NetLogo web, and this is somewhat new, but it works really well in that. So this loaded an example model, which you can see here, but you can generate a new model, you can upload a new model, and basically, I'm not going to go through this particular model. It happens to be the one that showed up, and it's got interface elements, it's got sliders, buttons, graphs. We haven't seen those, but all that sort of stuff. Command center. So there's a command center in here that I can use just like we do normally. So I can say CR05 or 4, and there are 4 turtles. They're really tiny, but they're there. And so you can interact with NetLogo on the web if you ever have problems running it on your own machine.
Will you be able to save it? Or
yes, you can save and download. So you can export as a NetLogo file or an HTML. It'll do. This is all done in JavaScript, and so it exports it really nicely. So this is another great resource, part of NetLogo. All right, so that's how to learn more and how to do more. Now I want to go to image. Sure. So the next thing that I wanted to hit on is what can be done in NetLogo? Probably the most popular question we've got. What can you do here? And NetLogo comes prepackaged with a host of programs, actually. If you go to what's called the models library, you get this window here, and all of these folders contain a number of models in all of these fields, right? So if you're a teacher right now looking and you're not a computer science teacher, but you're a chemistry or a biology or earth science or whatever, you can say, oh, there might be a cool model here. And so like here's chemistry and physics. There are a few that I know will look okay if... Where did
turbulence sounds promising.
Yeah, turbulence.
As does gas chromatography.
Waves, that's what I wanted. I just wanted ones that I know like display nicely and things like that. So here is a demo called rope, and this is a physics thing, right? What happens when you wave a rope around, and this is all done in NetLogo, right? These are all turtles that are moving. You can see the wave moving, and then you can change things. I can change the frequency with which the person, well, let's reset up. There we go. Changing the frequency to something that high makes it a little bit harder to see, but you can definitely see the wave propagating, and then actually the wave back propagating, right?
Yeah.
I'm not a physics teacher, so I can't do a good job of explaining all of this, what's going on. But here's an example. It's a physics simulation done in NetLogo with turtles.
It also takes an abstract concept and helps you visualize it using the algorithm. So it really helps you
Yeah.
understand the concept of what a wave is, how it works,
Yeah.
and you can manipulate it.
Yeah, exactly. And you want to know how it works? Here's the code. It's all here. Notice it's not a lot of code. I scrolled through the entire thing very quickly, right? It's all there for you to look at, learn the algorithms, figure it out. I just want to show a couple others just because I want to show the variety of things that you can model in NetLogo. So we will go away from chemistry and physics. You might say social science. That's not really a computer science thing.
Don't get down on the social sciences.
No.
They're very sensitive. They
No,
like
well,
to consider themselves a genuine science.
Yeah, and the thing is, computers can be used to help learn things about social sciences. We can model stuff. There is, trying to remember which one I decided. Oh yeah, it's up here. Social sciences. Cooperation, there it is. Cooperation. Let's make it a little bigger. So in this model, we've got cows, right? The blue cows are greedy cows, and the red cows are not greedy. They're cooperative cows. And they model basically the green is grass, and the cows eat the grass. If there's not enough grass, the cows die. And the greedy cows eat too much grass. The cooperative cows don't eat the grass if there's not enough for the grass to regrow quickly. And so that's the idea. And we can move all of these sliders around, but if we just do the default state and we click go, right, you can see the grass being eaten, and the cows start moving around, and we've got this graph, and eventually, so we've got a lot of greedy cows, and they are running out of delicious grass, and the cooperative cows are also sort of running out. And we could run this for a while. We can change parameters. We can see what happens, like is it better for a cooperative behavior. And I'm running the model again. And this time you'll notice that restarting it, it seems like the cooperative cows are doing a lot better. Right? So it's not like run it once and, oh, that's the answer. Run it a bunch of times. See what's going on. All right, so this is really about cooperation. It's not about a physics or a sort of hard science principle. And we can model that. And so I'm just going to I'll show one other model here, and then I want to show some things that my students have made.
While you do that, I'm going to give a shout out to Bodine for tuning in. Thanks, guys. We love having you. Make sure you ask us some questions. Questions have been a little quiet. If you've got questions about computer programming or anything involving computer science, JonAlf is the guy to ask, and he is here to answer those questions.
Yes. So this is sort of, if you do NetLogo, it's kind of the quintessential NetLogo model. It's called flocking. And it's
called what?
Flocking.
Well,
flocking.
I had to make you do it twice.
Yes, I know. And it's supposed to model how birds form flocks that go in a designed order. And the interesting thing is you might think, oh, this happens because the birds have selected in some way the head bird and they're all going to follow them, or they all know to go in a particular direction. It's actually more interesting than that. Basically, every bird has their own set of instructions, and the instructions are, if there's a bird close to you, kind of move towards them. And so we start out here with a whole bunch of birds randomly aligned. These are birds. They look like triangles. They're birds. And they move around. And as they move, they start to form flocks. It doesn't immediately occur, but you'll already notice we have set patterns here, right? And so this is what happens when you have a whole bunch of agents that are performing the same action. They're performing the same individual action. None of them are saying, I'm going to follow this bird. They're just going to say, oh, if there's a bird near me, I'm going to kind of move towards it. And naturally, this idea of a flock appears. And now we can see almost the entire screen. We started with 300 birds. Almost all of them are moving generally in this direction. And they formed these clumps. And we can do things like say, all right, how easy can a bird see other birds? I can increase that value. having some clicking problems. We can decrease the amount of separation that a bird will tolerate. And notice, immediately those flocks compact, right? This is part of the power of NetLogo, is generating these models that you can manipulate and interact with and learn, right? You could not learn about computer science right now and just learn about how birds generate flocks. And that's cool too. And you want to know the code, here's the code, right? Once again, not a ton. Yeah, it's dense and it's complicated, but you could learn this. You pick, all right, how does this work? How do they do this? Mess with it, right? And if it breaks, that was another question we got a lot. What happens if you mess up? It's fine, right? If it breaks, you reload it and it's back, or you fix it.
It's just text commands on a screen.
Yeah.
And so you can delete them, you can save them, you can try multiple iterations. We do have a question from the audience.
Great.
So here we've got birds as triangles. How good can you make the graphics for your creations in NetLogo?
That's a great question. There are a number of built-in shapes. We've seen the turtle and the cow, and they're not perhaps as detailed. But you can actually generate your own shapes in NetLogo. There's a shapes editor that you can draw, and you can do decent graphics, right? It's not going to be the latest 3D engine, but it'll look nice. And I'm going to show some programs that my students have made, and they really do enjoy making nice graphics, and so we'll see those.
Yeah, I mean, these triangles, we're calling them turtles, we're calling them lots of different things. They're really just to show, to demonstrate the potential, to demonstrate how it works.
Yeah.
But you can do more nicer things, and you're going to show us some of them.
Yeah, exactly. So, so these are the sort of built-in things that are there with NetLogo. There's also, in case you didn't see it there, there's a section for games. There's a Pac-Man game, right? You can learn how to program Pac-Man and play it and modify it and whatever. So when I teach NetLogo in my classes, at the end of the semester, all my students have to make a final project. Some of them work in groups, but they all make a project in NetLogo, and it's very much whatever they want. And so I wanted to show some of the things that students can make in NetLogo. And be like, oh, well, I can't do this. Sure, you can. So now, some of these are, really some of my top ones, but they're still cool. So, oh no, I didn't want to start with that one. No, you didn't see that.
Save the best to the end.
Yeah. What did I want? Let's start with this Arkanoid. All right. So this looks like Arkanoid, and we can see this was made by Jason because he made this little splash screen here. And I'm going to play it. I'm going to do new game. Looks like Arkanoid. And I'll click go. And I've got my paddle. It follows the mouse. I hit the... And I'm going to do this. I'm going to play on a trackpad, so I'm going to be bad.
How old is Jason when he made this?
Jason probably was around 14. He was a sophomore. So I think that's about the right age.
And is this one semester's worth of work?
Yeah, this is one semester, putting together. So things to be aware of, right? The paddle and the ball and the bricks are all turtles, and they are custom shapes for the turtles. And when the power-ups come down that I have successfully missed every time, those are turtles. And so this is, and then I just lost a life. And he built
it to be tough.
Yeah, and win this level in case I just want to magically go to the next level.
He didn't build it to be that tough.
Yeah. Well, it's nice. You don't want your teacher to be really frustrated when they're playing your game and grading it. And you're like, oh, this is a great game, but I can't win. Well, so here we go. Arkanoid, it was built off of, I want to build this thing. So that's Arkanoid, built by a student. I have... here we go. This one is popular Angry Birds. So loading an image. There's a lot of information about how to play. And let's see if I load sample level. So we see we've got our birds. We've got the pigs hiding out just like in Angry Birds. I click play and we're all ready. So actually play loaded a different level, which is fine. And then I click fire. And what's going to happen is I'm going to put a bird in the little slingshot and pull it down, and there, that was not nearly far enough. And I can do S. You'll notice that there were letters there. I pushed S to trigger that button.
And again, the birds are turtles.
Yeah.
And you've got an algorithm that's saying how the slingshot's going to work, and there's math that determines that.
Yep.
And it's variable. You can change it.
Yep.
So and all of this is custom designed. Yeah,
and so I'm going to do a better job. I have failed at using the trackpad. Oh, now too far. I'm not going to hit the pigs. That's not going to happen. There we go. This is Angry Birds, and this was built by a student a few years ago. Her name was Batya. Right? There was a question about are girls in computer science. I've got a lot of really wonderfully talented girls in my classes. One of the best things that we've done at my school is make the Intro to Computer Science course required for all sophomores. And so people who never thought that it was a thing for them all of a sudden realize, hey, this is cool, I can do this, and it's a wonderful way to get everybody involved.
So do you think that should be modeled in more high schools? Do you think every student should have at least one semester of computer science just to understand algorithmic thinking and how these systems work?
Oh yeah, computers aren't going anywhere. And the more technologically literate you are, the more you're comfortable with the computer and how these programs work, the better you're going to be at just getting by in society. And algorithmic thinking, computer programming is a useful tool, right? That's something that I've tried to stress, is that it's a tool to help you do other things, no matter where you end up. And so, yeah, making a required, I know there's a lot of outreach to get that to happen in the country now, but there should be more, because it's wonderful. And it's tough. It's tough to be a teacher sometimes, and you want to be a computer programmer, and I want to make games. Do I want to teach? And it's but it's a wonderful option.
Show us one more example.
Yeah.
We'll get Will Greenwald out here to talk about robots.
Exactly.
And do some demos of robots and talk about how programming affects lets you control these robots.
Yeah. So this was made just last year by two students. We've got Ryan and Kevin here. The previous one, the Angry Birds, was made by Batya. I forget if I mentioned that. And that was my fault. That's not their fault. Dismiss. November 9th. I will do setup. I'll do screen. Oh no.
Again, worst possible scenario.
Worst possible scenario.
But not the end of the
right now. But I'm going to open this because the iPhone simulator is pretty cool. Right? They came to me and they said, we want to make an iPhone simulator. And I thought, all right, guys. They were really good. And I said, they proposed it to me. I said, all right, if you think you can do this, then we'll get there. iPhone. Set up. There we go. Okay. I don't know what happened. So it looks like an iPhone. Screens. There. Look, there's a power button, which they've labeled, which is helpful.
Sure. Yeah. In
it's
case
hard
you've
to
never
see.
seen an iPhone before.
Well, maybe I want to try the top. So I push the power button, it shuts off. I push that.
That's cool.
I slide to unlock. Touch code. I believe, nope. It was 0035. And yes.
That's not what you actually use.
No. That's not my iPhone password.
Just important to remember.
Yeah, that was the one that they had set up. And then we have apps, right? Like, this is great. There's a clock. And what time is it? It's about this time, right? It is 11:28 or so. They've got the right time. I click the home button. There's a little notes app where you draw your note instead, but that's fine. Hi.
So, and the lesson here is that this is through the app, through building this simulator, they're actually going through all the same steps that Apple engineers do to build the original apps.
Yeah.
I mean, there's obviously a lot more code, it's a little more complicated, but just that functionality, they can simulate in NetLogo.
Yeah, and that's one of the things NetLogo is great for, is prototyping, right? You're not going to write the iOS in NetLogo, but they prototyped what they wanted it to, how they wanted it to look, what they thought it should do, and they did it very, quicker than you could write iOS. Here's a subway map because they live in New York, and the subway map is super useful, navigable, which is great. And because what phone is complete without a game, they programmed Angry Birds into their iPhone simulator, and so yeah, and there we go, and So I keep dying in Angry Birds, but anyway, this is just a smattering of things that can be done in NetLogo, things made by high school students. And if you're younger in high school, not younger than high school, that's still fine. There is still a lot you can do in NetLogo using the resources I showed earlier today. And I've been really happy to be here and show NetLogo. And definitely wanted to make sure that people could see the possibilities.
Very cool. And we will post links in our coverage on PCMag.com for all those sources, for those websites you talked about, where you can get all those resources and access. We've got a question from the audience.
Sure.
What do you think would be the next step for someone who wanted to keep progressing in NetLogo?
So the next step would be really, depending if you don't have a class where you might learn this in class, I think look through some of the models, the sample models that are there in NetLogo, and look for one that you find interesting, and also look at the code and look for one that's not super dense, right? And figure out what it does. You've got the NetLogo dictionary to learn the pieces and modify it. I started learning computer programming by initially modifying HTML for web pages, which is a little silly thing, but like you do little modifications, you get more comfortable with the environment, and you learn more about it.
I think that's really a key message. When people go to NetLogo and they see that blank screen and they feel like they're starting from scratch, it's intimidating. It's like being a writer and you start with a blank page. But the truth of the matter is all of this code is already out there. There's a lot of code already out there, and you can learn from it, you can copy it, you can modify it, you can customize it, and just the process of doing that, I think, is extraordinarily instructive and moves you along really quickly.
Certainly, yeah.
So we're going to move to robots now.
Awesome.
Let's get Will Greenwald out here to talk to us about robots, which do involve programming.
Yeah.
Will Greenwald does our robot testing, our HETV testing, and you play with a lot of robots.
Yep.
So what have you got for us today?
Well, last week we talked about LittleBits, and basically it's an electronics kit that each piece you can basically look at as a programming term, as a command. So you have inputs, you have outputs, you make it do things. But the thing is, as a device, these are by default pretty not smart. Here I have this little bar graph. You can move it up and down with this slider.
So let's break down, in case somebody hasn't seen last week's show, what are we playing with here?
This is an electronics kit that uses a dimming sliders and bar graph LED, and this is a servo motor that it makes it move up and down. But that's not the real point here, because this is a pretty dumb device. You need to control it directly. What's really interesting and really folds this all back into programming is this. This is the Arduino Bit. It's the LittleBits version of the Arduino microcontroller, which is it's basically a tiny computer. You can get it for about $40 and it lets you program it to do pretty much anything with different devices connected to the input and output pins. In this case, instead of needing to use a slider, I entered a code, which we're going to put up here.
Got you.
Yep.
There you go.
And as soon as I switch it, it does it automatically. And this is one of the simplest codes you can do with Arduino. We can show it, if we can get in close right there. The analog write command writes to the 5 and 9 pins, these two parts, and it basically sends out a signal that makes the bar graph go up and down and triggers the servo. And all this does is just counts up and down and make it move back and forth using different outputs. This is one of the simplest things you can do with Arduino, and the Arduino LittleBit is one of the simplest to work with Arduino modules. But if you want to get really, really interesting with this, you can take LittleBits out of the equation or augment it. There are actually solder pins on here too, so this is very expandable. And start working with Arduino and various components. It's a powerful, well, not powerful in terms of like computer power, but powerful as in what you can do with it. You can program it to do almost anything. The language is a bit more complicated than NetLogo. The syntax here is kind of similar to C, C++, Perl. And it does need a bit more expertise, especially if you want to do any soldering on here or work out circuits. But when you can, all you got to do is plug this into your computer, upload code, and you can have it do any task.
So give us some examples of those tasks, like
Well,
flashing lights, we're running motors.
Well, I have a servo motor right here, and the servo motor is sort of the key to how robots work. It basically moves all the joints because it's a motor that runs across a limited range of movement, so you can have like an arm move a certain amount. It doesn't just spin like wheels. And you can have a bunch of servos working in time according to a program teaching it basically how to walk or how to move a hand. And if you add sensors, if you have like a light sensor or an infrared sensor, you can control it with remote controls and have it say, press this button, it starts walking. Or if it sees something in front of it, it stops. There are a lot of really interesting projects you can do with Arduino, especially because the board itself, it starts very cheap. You can get it for about $40, but you can add pretty much any electronic component from just resistors and transistors and motors to entire shields and expansion boards that add Wi-Fi connectivity. like much more servo control, like robotic intensive devices. You can do a lot with this.
So
and
John, have you used products like this? Have you used LittleBits and built systems?
I've done some stuff with Arduinos before. There's another, it's a much more robust, it's a little computer basically called a Raspberry Pi, which is about this big, and it's an entire functioning computer. And these things are great. I want to point out, because we've got this code, people have been asking what other languages are there, and I've said there are features that are the same in all languages. And so I just want to point out a couple things that we've done, right? We did procedures in NetLogo. And if you look, there are two, they're more called functions here, but the idea is everything from this curly brace to that curly brace, this is the code for that function, for that procedure. And we saw in the first session the repeat loop, right? Something that happens over and over again. Well, here is a loop in C, or the Arduino language. It's this for thing. And it says for, basically this says go from 0 to 255 and repeat. And so those are things that happen in all the languages, right? Loops, there are no conditional statements here, but they exist in this program, rather, but they exist in the language. And so that's, I'm glad that Will's showing this, because you can start to see little differences in languages, but also the similar structures.
Raspberry Pi and Arduino seem very similar because they're both like really inexpensive sort of boards that you need to do a lot with yourself, programming them to get them to work.
Yeah.
But really, Raspberry Pi is a fully functional computer that's very inexpensive. You need to work harder with it to get it to do anything. But it means you can work a lot more with it for very little money. Arduino is much more device-oriented. There's input and output pins, so you can add components, and it's basically for building things like robots. And they're both, they're less accessible than NetLogo because the programming for both is more difficult. You need to go deeper into the subject, but they're inexpensive ways to get into both computer science and like programming robots. And you know, they're
also
fascinating. They're
powerful. You're not starting from scratch, because a lot of these programs have already been written.
Oh yeah,
you can go online and find the code to do a lot of these processes and do a lot of these commands and then modify it.
Yeah, this script actually is almost entirely one of the demo scripts Arduino has for their Arduino LittleBit, because you need a special formatting for the pins that go into the bits, different numbers. But all I did was add 2 values, so instead of just making the LED bar graph go up and down, it also makes the servo motor move. And studying these scraps of code, and there are tons of samples that you can get for free online that basically let you understand, okay, this is what this code does. It moves a servo arm, it draws a picture, and then you can say, okay, how do I want it to move my device or draw my picture? And it gives you stuff to play with that you can build on, that you don't need to start entirely from scratch, which is really difficult.
Yeah, very cool. Well, guys, I want to thank you for doing this. This is going to be our last Hack to School for this semester. I think we've done a great job of sort of introducing the concept of coding, showed how to try to demystify the process, provided lots of resources for students so that they can get up and running. I want to thank Lenovo, Hack to School, our partner. They've been donating laptops to get laptops in the hands of kids so that they can start playing around with these tools. Thank you so much, JonAlf. Thanks so much for coming in.
Thanks for having me. I've really enjoyed doing this. Thanks to the school, spending time, showing these videos and sharing CS with their kids. It's a wonderful field, and anybody can do it. So I hope people pick that up.
The stream is going to end, but we're going to be keeping this on Facebook forever. We're going to post it to YouTube, and we will have content on our site with all the links. Thank you so much for joining us. Thanks for tuning in, and tune in next time. Hopefully we get even more Hack to School in the next semester.
Yeah.
Thanks for tuning in.